Okay, so today I want to just know how much we know about free energy. I want to see how many of you have heard this term. All of you must have heard. Let's see what is your understanding of free energy.
It's the energy of the system which is available to perform some work.
Some work. Okay, so that's the reason why we call it as a free energy. And Gibbs has defined it, as you all are aware, as G equal to H minus Ts. This is something every one of you should know and must have gone through it, where H is the enthalpy and T is the temperature and S is the entropy. And this also coupled with the other equations, this comes actually from the second law of thermodynamics, all of you are aware of it, and because the entropy, concept of entropy is actually comes from the second law. First law basically talks about what is first law? How many of you? Conservation of energy is the first law. Okay. For example, H equal to E plus PV. This is what we call it as the first law. This is, let's say one way of calling the second law, if you want to say, and then we also have something called a third law of thermodynamics. How many of you are aware of third law? What is third law?
So every substance has zero entropy at 0 Kelvin.
Correct. So entropy S tends to 0 as T tends to 0. This is what is third law. This is what we say. Am I right? And there, one point that you all have to remember, whenever we say entropy, which is basically entropy is the degree of randomness in a material, and this degree of randomness can come into a material because of two important factors. One is called thermal, another is called configurational. For example, at any temperature there are vibrations inside a material, and these vibrations would cause some kind of randomness inside the material, and that particular randomness that you see is what is referred to as thermal entropy. And we define that particular entropy in terms of, how many of you know this? How is entropy defined? Yes, in fact, if you see the second law definition of entropy is ds equal to dh by t, or we can, it also comes out as q by t. Actually this is how the first at the beginning people have defined the entropy, and because we know under certain conditions, under what conditions q can be taken as dh? Constant pressure. So we take it as dh and it becomes dh by t. And H in principle, enthalpy is related to what? Internal energy. Okay, H equal to E plus PV we have already written, but how do you measure H? If somebody wants to calculate the enthalpy of a material, how does he? From the specific heat. So H is nothing but integral Cp dt from anywhere, from 0 let us say to some temperature T. So H is integral Cp dt, and basically Cp is what we know is the heat capacity of a material at constant pressure, and that is basically nothing but the amount of heat. How does one define the heat capacity? Tell me.
The amount of heat which a material can hold for a degree rise in temperature.
Correct. Not hold, the amount of heat that is required that it needs to raise the temperature. That is how we define. And once we define H as integral Cp dt, S automatically turns out to be, because ds is dh by t, so you can see that S is nothing but integral Cp dt by t. Okay. So these are the basic equations that one need to remember when we are talking about the entropy and the enthalpy. And in principle one can even find out how the entropy increases with the heat capacity. In fact, if you carefully observe this, the heat capacity of a material itself is not a constant term. How does heat capacity change as a function of temperature, do you know? Increases with temperature. What kind of a shape it has? If I plot, let us say, heat capacity as a function of temperature, how does that plot look like?
Hyperbolic, like S shape.
Yes, it starts like this and then saturates somewhere, and this value where it saturates is what we usually take it as how much? Some of you have remember from your earlier studies, it is 3R. One can derive that and show, and as you can see that Cp actually goes to 0 at absolute 0, because there are no vibrations at absolute 0. Heat capacity comes because of the vibrations, and because the atomic vibrations vanish as you go to 0, the heat capacity goes to 0, and that is why you will see the entropy also actually goes to 0. That is what is third law of thermodynamics. So you can see that the Cp more or less is very small and then it increases, and as a result, because this increases, if I try to see what is ds by dt, that means the rate of change of entropy with temperature, that can be given as what? ds by dt will be Cp, it will actually turn out to be Cp by T. So that means you can see that the rate of change of entropy with temperature is Cp by T, and that means the entropy always increases with increasing temperature. When I say ds by dt, how does the entropy change as you increase the temperature? Is it positive, is it negative, or is it does not change? If you look at it, if Cp was 0, then we can say ds by dt is 0. ds by dt being 0 means what? That entropy does not change with temperature. At any temperature, material will always have the same entropy. And again, I am talking in terms of the thermal entropy here. We have not yet come to what is called configurational entropy. Configurational entropy comes into picture when you take more than one type of atoms and try to put them together in one place, like something like you take a box and try to put red balls and the white balls together, certain number of them, and depending on how you can arrange these red and white balls, there is some randomness associated with that particular configuration, and this is what we call it as a configurational entropy. And you will see slowly as we go along, materials which are ordered will have very low configurational entropy, and in fact one can even prove that if a material is perfectly ordered. Have you heard of ordered compounds? For example, sodium chloride is an ordered compound. You will see every sodium will have a chlorine atom around it, and every chlorine will have a sodium atom around it because of the ionic bonding. You have also in metallic systems also you have intermetallic compounds. Okay, things like if you have heard of compounds such as Ni3Al. Do you know where Ni3Al is very important? Superalloys. The strengthening in superalloys basically comes from that particular phase which is called gamma prime phase, Ni3Al. Ni3Al is ordered, and if it is in a perfectly ordered condition, an ordered material also can have some disorder inside it. We call it as partially ordered. If it is perfectly ordered, then in such a case we can prove, as we go along we will do it in this course, that we can prove that it is actually will have 0 configurational entropy, and in that case the material can only have one more entropy, which is the thermal entropy. Thermal entropy is bound to be there whether it is ordered or disordered structure. Only difference between the two is if it is perfectly ordered, it will not have a configurational entropy, it will have only one type of entropy, which is a thermal entropy. Otherwise, if it is disordered, it will have both of them. And for a pure metal, if I am considering, in principle I will not talk about configurational entropy, because there is no second element there. In fact, if you go deeper, people even talk in terms of the vacancies inside the material and talk about configurational entropy arising because of the presence of vacancies. But in general, for normal study, we usually consider for pure metals that only thermal entropy becomes dominant and configuration entropy does not come into picture. Only when I add a second element, a binary system or a ternary system or a quaternary system and so on, we start talking about configuration entropy. So,
in case of NaCl existing at room temperature, will that be perfectly ordered?
it is ordered, of course. In fact, particularly in ionic solids, if to introduce a disorder into them is not so easy. For example, if you want to remove one of the chlorine atom, the bondings are disturbed. You need to maintain what is called the charge balance. And if you cannot maintain the charge balance, you are in, the system is at a higher energy state. So in order to keep the system at the lowest energy state, system prefers to have every sodium atom would like to have a chlorine atom around it because of the shape, basically the exchange of electrons in that particular material. So you would see that when I am talking about the thermal entropy, you would see the thermal entropy, because Cp is positive. Cp is never negative. We have seen from here, Cp, the lowest value Cp can take is 0. So that is at absolute 0. At any other temperature, Cp has a positive value. If this is positive, then this ratio is positive, isn't it? So this particular, rate of change of entropy with temperature is always positive. So entropy increases with increasing temperature. And what is the rate at which it increases depends on the material. For some material which has a high Cp, you would see that it will have the rate at which increases is higher. You will have a steeper entropy. If I plot entropy versus temperature, you would see a steeper curve there, which we will see it possibly in the next class as we go along. So this is something which you need to understand before you start discussing about the free energy. I think with that we will stop for today.
Can we induce configurational entropy by increasing the temperature? As in like NaCl, if you increase the temperature, the bonds start becoming weaker, right?
Correct.
So the order might not prevail at a certain temperature.
True, but that particular entropy that you are getting there can also be talked in terms of thermal entropy. So that's why it's a little tricky issue to say this particular entropy that is generated in the material, is it because of thermal or not?
Because of thermal we are inducing the configuration.
That's right. Configuration entropy is assumed to be constant once you have fixed the amount of the second element. As you go along, you will see. How many of you remember configuration entropy expression? KLNW, and the KLNW, if you derive it further, it turns out to be minus R xi ln xi. For a binary system, we can easily show that it is delta S configurational is nothing but minus R xa ln xa plus xb ln xb. Some of you might have seen this. And you can see that this is a function of only composition. And once you fix that, and in fact you can clearly see that this would obviously go to 0 when you go to a pure metal side. If you put any one of them as 1, either xa as 1 or xb as 1, you would see immediately that the function goes to 0. So that is why configurational entropy is 0 for a pure metal, and it comes into picture only when you have more than one element. And in principle, if it is more number of elements, we write it as xi ln xi, where I equal to 1 to whatever it is n. So any number of elements you can continue that expression. We will talk about multi-component systems as we go along, and there you will understand as we go along. Okay, we will stop now.